Carter and Tommy's Chapter 13 take-home test. So the first step we did, we defined each x, y, and z term as its own function because it makes the solving the derivatives easier. And then we defined that curve of f of t, g of t, and h of t, where we then made a point on that curve with the slider k, and then made the tangent vector by just making a vector from r of k to r of k plus the unit vector of the derivative of r, because that's the rate of change and gives the direction of the vector. And then we made a unit vector to have a nice uniform length. And then from there, we started working on the tangent vector. So we made a new curve. Basically, it's the derivative of r, f prime, g prime, h prime. And then we made the normal vector from that. We did the vector from r of k to r of k plus the unit vector of the derivative of a, because the normal vector is the derivative of the tangent vector. And then lastly, we made the binormal vector, which is the cross product of the normal vector and the tangent vector. And then you just had to make sure, again, it was from r of k to r of k because you want to make sure it's a point on our curve r. Then we used the curvature function to define kappa, where we used r of k and r of t to basically just solve for kappa. And then we made the center of the circle because the center of the circle is a plus rho n. Rho is also 1 over kappa, so a plus n over kappa gives you the location of the center of the circle. And then lastly, we made the circle with the center c. The radius is c minus r, or that distance from the center to the function. And then finally, for the direction circle, we use b, the binomial vector, because it tells it which way to open.
The red vector we have here on the circle, it is tangent to a point on our original curve for a given value of t. And it shows us the direction of motion that we will move in as we increase or decrease k. And then the green vector we have here is perpendicular to this tangent vector, and it shows us the direction that our curve is bending in. And as we can see with our graph that we have plotted here, it is always bending inwards towards the center of the circle. And the purple vector we have is perpendicular to that green, to the circle used to represent the curvature of the graph. And this purple vector kind of shows us the plane in which the curve lives in, as it's the cross product of the normal vector and the green vector.
Mm-hmm. And then we're questioned, so why does a circle necessarily have to have tilt? And it's because when we define the circle, you have to give a direction of the circle, and you use b, the binomial vector, the direction of the circle, because for the other two vectors, they're both in the plane of the circle, so just using one of those vectors doesn't necessarily tell you which way it opens, but the vector b will always tell you basically the way. If you make a plane on the circle, it shows which way the plane is facing. And thus, since our binomial vector is clearly tilting with the function, thus the circle also has to tilt.
Here on our graph, we have a big K value. As we can see, our circle is very small, showing that it has a high turn radius, giving it a high curvature. As you know, we follow the curve and it's bending very quickly and sharp. Here we have a small curvature. As we see, our circle is much bigger than previously, and if we just even follow the circle, we can see that it is curving a lot slower than when the circle is small, giving us a lower K value. And using this circle to find the curvature is a lot better than using a line, because a line doesn't necessarily show us the curvature, as the circle has a radius which can help us find this curvature and how fast we are curving.
I like Big Kappa and I cannot lie. You other fucks can't deny. When you take the inverse of the value rho and you know it turn real tight on that graph.
With that sharp bend, because you notice that radius small, changing the tangent vector is tiny and won't stop turning. O-T of T, I differentiate. Respect to arc length, my classmates tried to warn me that Kappa you got makes me so curvy. Ooh, radius shrinking, you say you want to show me that bend? Well, graph me, plot me, cause you ain't a linear function.
That tangent swinging, it takes a little thinking to see. Find the way it moves about. I'm tired of textbooks saying small kappas are now banging.
Take Gucciovin and ask him that, he'll tell you that straight cap. So, functions.
Yeah.
Functions.
Yeah.
Every variable's got the curve.
Heck yeah.
Graph it.
Graph it.
Graph it.
Graph it.
Graph that bendy curve. Baby got kappa.